Hi, this is Riddhi Tanno and my lab partner is Vishwa Shah. And today in this video, we are going to explain the 10th lab of CS302 Modeling and Simulation. In this lab, we are modeling the spread of forest fires. So these are our model assumptions and parameters. So in the assumptions, we are taking that uh, an empty cell will be represented by 0, and a cell that contains a tree will be represented by 1, and a cell that is burning will be represented by 2. So we are modeling this using cellular automata. So we will have a grid containing cells, and this is what the cells would be representing. And the second assumption is that a tree can be burnt by its neighboring trees, or if a lightning strikes with a certain probability, which is 1 minus the probability of immune. Now I'm going to explain what the parameters mean here. So the first parameter that we have is probability immune, which is the probability that a tree is immune from burning by a tree or by lightning. The second probability that we have is the probability of lightning hitting a site. So when lightning will hit a site, that site, if it contains a tree, it will be set on fire with a probability 1 minus probability immune. And then the third parameter that we have is probability burning, which is the probability that a tree is burning initially when we start the model, when we start the simulation. So, and the fourth parameter that we have is probability tree, which is the probability that a site is initially occupied by a tree. Now, here is one simulation where we model the basic model with periodic boundaries. So, as I mentioned earlier, we can see at time is equal at the first time step initially. So these are our parameter values. First of all, the probability that a tree is immune from burning is 0.25. Probability that lightning will hit a site is 0.00000001, which is very less. The probability that the tree is initially burning is 0.0005, and the probability that a site is initially occupied by a tree is 0.8. So that is initially to essentially to say that 80% of the grid will be occupied by trees initially, as is the case in this simulation. And since the probability that a tree is initially burning is very small, we can see that one tree is initially burning. Now, when I play the animation, we can see that because of that one tree, after we reach equilibrium at time 31, a lot of the forest has been wiped out due to the fire that one tree had caused. Now, let us see what happens when we increase the initial density of trees. So by initial density of trees, I mean that we increase the probability of it being that probability that a site is initially occupied by a tree. So these are the probabilities for which we simulate. Okay, so so this is basically saying that 10% of the forest is covered with trees initially, 20% is covered initially, and so on till 90%. And we do the simulation for two burning probabilities. That is, now in the first case, we assume that 0.005 fraction of the forest is on fire initially, and in this case, even a smaller fraction, 0.0005, is on fire initially. Now we can see that at when the initial density is 0.1, the final density of the trees is somewhere a little bit less than 0.1. When we go to 0.2, the final density is again somewhat less than 0.2, but it's still near 0.2. And as we move further, it is the same until 0.6, where we see that the initial and the final density are somewhat similar, after which at 0.6, after 0.6, so from 0.7, 0.8 and 0.9 onwards, we can see that the final density of the trees is very less as compared to the initial density of the trees. So we can say that 0.6 is our tipping point in this particular model when the probability of a tree initially being burning is 0.005. So this is basically to say that 0.6 is our tipping point in this particular model. Now when we move on to the probability burning being 0.0005, our tipping point moves further away to 0.8. So this can be explained by saying that a lesser fraction of the trees is burning initially, and hence it takes very long, or it takes very long, or sometimes it won't even completely wipe out, or so a lot of the forest will not wipe out. So, and in this case, since the probability of burning is a little bit more, the tipping point is earlier, and after the initial density of trees being zero point 0.6 or more, we can see that a lot of the forest gets wiped out. Whereas here, you need more initial number of trees for it to wipe out. Um, So this is one of the simulations of probability burning being 0.0005, and here we take that take the case that initially 90% of the um, grid is occupied by trees, and so you can see that one of the trees is initially burning, and now we take very lesser time to reach equilibrium as compared to the case where the probability of tree was zero point 0.8, which means 80% was covered. So we took more time to reach equilibrium, whereas in this case we are taking lesser time to reach equilibrium because there are more number of trees now. Okay, so now this is the project question 9, where we are changing the burn probability, and we're checking how much of the fraction of the forest gets burnt. So here the other conditions or the other parameters are equal to these respective parameters. Now we can see that 90% of the initial grid was occupied by trees. So burn probability is essentially the probability with which a cell will burn if its neighboring cell is also burning. So if the burn probability is less, we can see that lesser fraction of the forest is getting burnt. And as the probability goes up at zero point 0.9, we can see that almost the entire forest gets wiped out because there is a very large probability with which the neighboring cell will be burnt if a particular cell is burning. Vishwa will go ahead and explain exercise 1.
Moving on to exercise 1. So here we simulate the forest fire for a case where the time required for a tree to stop burning increases from one time step to two. So in this case, there are more chances for a fire to spread, and such a condition where a tree requires a lot of time to burn completely can prove to be destructive in real cases. We now run the simulation and see how the forest spreads quickly. In this case, the fire spreads quickly. Yeah, so as we see, after 22 time steps, we reach an equilibrium, and almost all of the cells have been wiped out and have become empty. We move on to question exercise 2. Here, we change the probability of the tree to burn in a particular cell. The tree will burn with a probability which is based on the number of its neighbors that are burning. So, to say, in all the above cases we considered, we know that the probability of immune is 0.25, and hence a tree will burn with a probability of 0.75 if any one of its neighbor is burning. Now, in this case, a tree will burn with probability 0.75 only if three of its neighbors are burning, and our thus the probability of a tree to burn decreases with respect to all the previous cases, and hence after a short duration we reach the equilibrium, and the spread of fire stops. We now run the simulation. So as seen, after 6 time steps, the burning stops completely. So that's it for our lab 10. Thank you.